Okay, hello everyone. We've actually got kind of an interesting topic today in that you already know part of what we're going to be talking about. You learned about power a few weeks ago, and now we're going to be talking about electrical power, specifically the power generated or used by some device that is in a circuit. So let's refresh our memories on what power means. Okay, it was right at the end of the energy unit that we talked about this. We said that the definition of power, the equation definition, was this. Capital P equals capital W over T. In other words, if you wanted to put that into words, not just letters, you have power equals work divided by time. P being the power, capital P being power, W being work. Remember, work is just change in energy, and little t, of course, being time. So, power is the rate of work that gets done. Rate of work done. And remember, whenever work is done, we can just say, you can substitute the phrase, or the change in energy per unit of time. Sometimes people mix up work and power, and that makes sense that they do that because the units of power are kind of confusingly watts, which is a capital W. Power is how quickly you do that work, the rate at which you do the work. Work is simply how much your energy changes, okay? They're not the same thing. Work is one thing, power is the rate at which work is done. The reason we're going to talk about electrical power is because the whole reason that we use circuits is that we use them because they can transport energy from one spot to another. So because they do that, we can find the rate of this energy transfer. We can find the power that they dissipate or give off. So, first question, what part of a circuit can dissipate energy? What part of a circuit can give off that energy and therefore have some power associated with it? Well, that's actually a pretty easy question. It is anything with a voltage drop. And remember, voltage drop just means if I were to hook up a voltmeter on opposite sides of some part of a circuit, is there a voltage reading? Okay, does the voltage drop from one of the probes to the next as we move through that circuit? So anything with a voltage drop gives off energy. Because remember, what voltage really is, the measure of voltage, anytime you're measuring a voltage, pretty much, you're measuring what's called a voltage drop, okay? You can measure just something called voltage, but it's very arbitrary. We are concerned almost all the time with what's called a voltage drop, okay? That's what you've been measuring this whole time. And when you're measuring a voltage drop, what you're really measuring is how much energy is given, is released, or how much the energy changes divided by how much charge a particle that is moving through that circuit has. The energy per charge, okay? So, if we think about what has a voltage drop associated with it, well, batteries have a voltage gain, so we're not going to list those, but resistors have a voltage drop associated with them, and they give off energy because we know that they give off heat. That's the point of a resistor. It dissipates heat. Matter of fact, last year, for the first time, I actually felt this. I had a student who had wired up a circuit, and their resistor, they had the voltage turned up pretty high. So when I went to touch the resistor, it was noticeably hot. I had never really noticed that before. So that is your proof that the resistors give off heat, okay? There's a voltage drop there. Energy is being dissipated. Therefore, we can talk about the power, the rate of change of energy that the resistor is associated with. Another one we haven't really talked too much about are light bulbs. Today we're going to talk about light bulbs, and if you take AP Physics 1 next year, you're going to talk a lot more about the power, which light bulb is the most powerful, okay? Light bulbs, as we know, give off both light and heat. And the last one that has a voltage drop associated with it are actually just regular old wires. Now you might be saying, well, wait a sec, we've never measured the voltage drop for a wire, and that's true. But remember, we did talk about how wires have very, very small resistances. And if they have resistance and they have a current going through it, therefore they have a very, very small voltage drop. Okay? Wires give off very tiny amounts of heat. We don't want wires to give off a lot of heat. That's why we make wires out of very low materials that have very low resistivities. I can show you this on the simulation. On this simulation right here, we have a battery connected to a resistor and a light bulb in series. I'm going to put the probes across the resistor to show that it has a voltage drop, and across the light bulb to show it has a voltage drop. Okay, and if I just put it across the wire itself, you might say, well, wait a sec, there's not a voltage drop there, it's zero. If I go over here to wire resistance and I take it from tiny, or basically zero, and I increase it, you see that you get a voltage drop, a slight voltage drop from the wire itself. Okay, and you can increase that. So wires can also have a voltage drop associated with them. Okay, let's get to our equations for power. All right, so in your reference tables, first thing I want to do before we get to the equations for power is I want you to recall Ohm's law. Remember, Ohm's law is the most useful equation when we're analyzing circuits. Ohm's law was V equals IR. Now, if we go in our reference tables to page 4, the electricity section, we're going to look at our last two equations today. We've done everything else on here. We've looked at series circuits, we've looked at parallel circuits, we've looked at all the circuit symbols, we know the resistivity table, we know every single one of these variables. Our last two equations are right here. And the first one we're going to look at is the second to last one. Okay? P, standing for power, electrical power, is equal to V times I. And you notice there's some other equations. I'll show you how we get those. So electrical power has the symbol P. And that's the same as mechanical power. That's what you can call this one up here. P equals VI. Now, I'm going to put that in a box because that's important. We can rearrange this. We can substitute in some other variables, because what if we're not given either the voltage or the current? Okay? What if we're not given the voltage? Okay, and we're asked, hey, what's the power? You might put this into a couple different steps. You might say, oh, well, I can figure it out using Ohm's law. Or let's do the Ohm's law work ahead of time. We know that for series elements, at least all the ones we're looking at, the voltage drop equals I times R, the current times the resistance. If we're not given the voltage drop, we already know that it's equal to I times R. So couldn't I say that P is equal to I times R times an I again? Which would lead me to saying P equals I squared times R? You absolutely can say that. So you can combine Ohm's law and the definition of electrical power. Or, and that would be if you're not given the voltage. Like, look at this equation. We're not told the resistance here, but maybe in some case you're asked to find the power. You're only given the current through some part of a circuit and its resistance. You can use this to find the power. Or what if you're not given the current, but you're given the voltage drop for some part of a circuit and that part of the circuit's resistance? Well, if we don't know the current, we can take this equation right here and rearrange it for I. I is equal to V divided by R. Right? Because if I divide both sides by R, I get V over R equals I. Couldn't I say this? P equals V times V over R. Which leads me to P equals V squared over R. Another perfectly good solution of the power equation that incorporates some of the variables from Ohm's law. So the point of this is that based on given variables, you can solve for P or anything else that you want to. Any of the electricity variables we've been working on with circuits. Okay? And just to check up again, P equals VI, that's the first one we had, equals I squared over R, also works, equals V squared over R. That's exactly what we found here. And again, if we know an object's power rating, so if we know how much power it gives off, we can actually kind of go in reverse. So what we've been talking about so far is the power as the energy per time. Okay? That's right up here. All right? And we can calculate that power based on voltage drops, currents, and resistances. If we then know the power and we know how much time something has been running for, we can actually find out how much energy it's releasing. because power is the energy released per unit of time. So, if the power is equal to work divided by time, or in other words, how much energy is given off divided by an amount of time, then if we solve that equation for W, the work or the energy given off, that must be equal to the power times the time. Again, where W is the work done or energy transferred, however you want to think of it. They mean the same thing. So if we know W equals PT, and we have all these equations for the power, then all we have to do is take the equations for the power, multiply them by T. So the work done, or the energy given off, could also be equal to VI T. Okay, since P is equal to VI, just plug in the VI there. Or it could be equal to I squared times R times T. Or it could be equal to V squared T over R. Each one of these works. It just depends on what you were given. So let's do a couple of these very quickly. Oh, actually first, before I do that, I'll show you where these are in the reference tables. Right here, W equals PT equals VIT equals I squared RT equals V squared T over R. So let's do a couple of these examples. A certain resistor has a voltage drop of 4 volts and a current of 0.2 amps running through it. What's the resistance of this resistor? Doesn't even have to do with power, right? We're given a voltage drop and a current. This should be easy to find the resistance. We use Ohm's law. V equals IR. The voltage drop is 4 volts. The current is 0.2 amps. We are looking for the resistance. 4 divided by 0.2 is 20. We get that the resistance is 20 ohms. Make sure you guys have the right units for these, because I know these units are a little bit different for you guys. I mean, they're not units you've been using the entire year, so there's a little bit of you're a little less familiar with them. Just to prove to you that this actually does in fact work, let me go over to the simulation. We have a 4-volt battery, which means there should be a 4-volt drop at the resistor, and a 20 ohm resistor. Oh, that's not what I wanted to do. We can measure the current when we cook these up. We said it should be, from the problem, it should be 0.2 if there's a 20 ohm resistor, and that is exactly what we get. Okay? Let's go back here, though, and let's talk a little bit about the power. What is the power dissipated by this resistor? You have your choice of whatever you want to use to solve this. If it was me, I would go with the variables that you were given. You were given the voltage drop in the current, and we know that power, electrical power, is equal to voltage times the current. So I'm going to use that. 4-volt drop, 0.2 amps. The power dissipated by this resistor, or the power generated, however you want to say it, 4 times 0.2 is 0.8, and remember the units of power are watts. So what that tells you, 0.8 watts is equivalent to 0.8 joules per second. This resistor gives off 0.8 joules of energy per second. Now the reason we want to know about the power of something is so that we can measure how much energy is given off. Because if you are paying the electric bills, you want to know, well, how much energy am I using? Okay, this is why we talk about things like power and electrical energy. All right, if this resistor dissipates power for 28 seconds, how much energy is released? We're looking for how much energy is released, or transferred, or in other words, the work done. We know the work. We know the work done. Again, there are many different ways that I could do this since I know the resistance, the current, the voltage drop, and the power. I'm going to choose the one that's simplest. The work done is equal to the power multiplied by the time. That means this is 0.8 watts times 28 seconds. And we end up with, after 28 seconds, 22.4 joules of energy were dissipated. Okay? We took electrical energy and we changed that into heat energy, and 22.4 joules of heat energy was given off by this resistor. Okay? You can tell this because if you touch the resistor, it would feel hot. Last question for this video. An electrical appliance draws a current of 0.5 amp and has an electrical resistance of 120 ohms. If it operates for 30 seconds, how much energy is released? Now, question B says, what is the power consumed by the appliance? And a lot of times sometimes people will like go and solve the second one first. You can solve these in any order you want. I'm going to solve them in the order they were given to us. We're told the current, we're told the resistance, and we're told the time. Okay? Based on that, we're asked to find how much energy is released. Again, that just means energy transferred. So, I'm going to go up here. Energy transfer is W, the amount of energy transferred. We're given current, resistance, and time. Current, resistance, time. That looks like a winner to me. Plug everything in with units. Oh, I did not square that. Good thing I caught that. Otherwise I would have looked pretty foolish. Probably already look foolish, but that's fine. Okay, we see that the energy transferred is 900, and remember, this is not power, this is energy, so it's 900 joules. Now, what is the power consumed by the appliance? Notice that power is just equal to I squared times R. Okay, so I could just do P equals I squared times R, and I would get, let's see, 0.5 times 0.5 times 120, which is 30 watts. Or I could use the definition of power. Power is work divided by time. The work done is 900 joules. That's how much energy is transferred in 30 seconds. Therefore, the power is 30 watts. Okay? Many ways that you can do these problems. We'll do the back in just a little bit.